So when we talk about sorting, we are essentially talking about a different problem. Searching simply means that you need to parse through an array and essentially look for where the element is. Now in the worst case, you just need to look at every possible position. But sorting, it means that you're given some array, which may come in random order, and then we need you to put it into an organized way, which goes either in increasing order or decreasing order. This is a more complex problem. Now, we are going to introduce two sorting algorithms. One is what we call insertion sort. This is still based on the linear strategy of actually solving a problem. Now, what do we mean by linear strategy? So let's assume here that you are given 5 cards, and the 5 cards, we know how to sort cards, right? So we know which card is bigger than another card. So generally we think that the color cards, like the Jack, Queen, King, so these are larger than 9, and Ace probably is the largest one. So suppose that we want to sort, and one possible way of doing this is that we go from left to right. So it's like linear search, right? It's going from left to right. And each time from the left, we try to move every card to the left to see whether we can move it to the right place. So in this case, 9 stays put because it's the first one. So the next card we're looking at is Queen. So we try to move Queen to the left to make sure that it's in the right place on the left. We find that Queen is already larger than 9, so that's already in the right place. So we move on to the third card, Ace. Ace is larger than Queen on 9, so it's already in the right place. But Jack here is actually should be somewhere on the left. It should be here between 9 and Queen. And we can take it out and insert it there. And for King, it's going to be between Queen and Ace, so we can take it out and insert it there. Now finally we're going to have a sorted array. Now the way this is actually working is this is the insertion sort in Python. Now it looks very simple, so we just have one loop, right? So which is this loop that goes from I equals to 1, and each time we plus 1, so it means we go from left to right. Each time we will look at the array and we try to move this element at I to the left. And when we're moving it to the left, we're going to make sure that it's going to enter the array in the right place. Now let's assume at any point that you already have the following array, where in this case your iteration is already at position 3. Now this part, at any point of time, if you're processing the I, anywhere from 0 to I minus 1 would already have been sorted. So this part is sorted. 0, 8, 9 is already sorted. And now we are trying to see where this element I equals to 3, which is 5, should be on the left. Now the way we do that is to compare to every element that is on the left. So 5 compared to 9 is smaller, so we're going to swap it. So 5 compared to 8, smaller, swap again. 5 compared to 0 is not smaller than that, so we're going to insert it there. Now this is done through this thing, right? So that means we're going to put it in between. So finally we have this left part that is already sorted. Then we can move on to the next location, which is I equals to 4. Then we're going to do this all over again. Now the move left method, what it does essentially is to move an element to the left. So we start with some point I, and I here, we are going to compare it to the left, and every time we compare, if it is smaller, we're going to swap. If it is not smaller, we will still decrement down until to the left. Right? Now, so this, we're going to look at a couple of examples to actually do this by hand. So let's say we have a starting array that is not yet sorted at the beginning, and we want to put them in a sorted order. So what it means is that we're going to start from the leftmost one, and as we're doing this, we're going to be counting how many comparisons do we actually need to do. So we start from the left to right. So the first one is 19. 19 here is already in the leftmost, so we cannot move it further to the left. So in terms of the number of comparisons we need to do is 0. So 19 doesn't need to be compared to anyone because there is nothing to the left, which is an empty space. Now when we process this 5, we will try to move 5 to somewhere on the left. And the left of 5 here is 19. So in that case, we have to compare 5 to 19. And because 5 is smaller, then we are going to swap them. Now at this point of time, this part is already sorted. And 5 required one comparison for us to figure out what is the right place on the left. Now the next thing that we're going to process is 16 then. Now 16, we have to go somewhere on the left. So we compare it to 19. 16 is smaller, so we swap. Then 16 is going to be here. 16 compared to 5. 16 is larger, so we don't swap. But even to know that we don't need to swap, we still need to compare to 5. Because if 16 is not larger than 5, then you will still have to swap. So which means that 16 requires 2 comparisons. And after this, the new array is going to look like this: 5, 16, 19. And we still have 2 more to deal with. So the next one is 17. Now how many comparisons does 17 need to do? 17 compared to 19, swap. 17 compared to 16, no swap. Only one swap, but 2 comparisons. So we still require 2. Now by then, the array is going to look like this. And the next thing we're going to process is 21. How many comparisons for 21? So 21 will only require one comparison, because you will compare it to the one immediately on the left, 19. And this is already larger than 19. So in that case, we can stop here. And your array in the end is going to be already sorted. Right? Now, these are the number of comparisons that we need to do in order to sort this array. Now, so we're going to start to look at what are going to be the worst case and the best case for this kind of algorithms. Now, let's say for insertion sort, to get a best case, we need to ensure that we're going to have as few comparisons as possible. So when will that happen? What kind of input array would we have such that we need to have as few comparisons as possible? Yes, Solomon. Already ascending, right? All right. So let's say we just take the following, right? So if you start from this as input, then now the insertion sort is going to work to go from left to right, and it's going to see how many comparisons do we need. So for 5, how many comparisons? 0, right? So it's already on the left. For 16, 16 is compared to 1 on the left, 1. Okay, how about 17? 1. 19, 1, 21, 1. So now for size n, how many comparisons do we need to do? So we're going to have n minus 1 comparisons, which means that we are going to have on in the best case. So that's the best case. We need few comparisons, and we still need on. Now, then what is the worst case then? So the worst case is if it is in the reverse order. Now, if it's in the reverse order, so if we take this same array but in reverse, now for the first element, how many comparisons do we need? We need 0 because you don't move, right? 19, 1, 17, 2. Because any number, it will require the number to travel all the way to the left, which means it needs to be compared to whatever has existed on the left. So the next one then will be 3, and finally 4. So now for size n array, we are going to end up with the summation that goes all the way to n minus 1. Now what is this summation then? So we do the pairing thing, right? It's going to be n minus 1. And there are going to be n over 2 pairs. So that is going to be the total number of comparisons we will need to do for insertion sort, which means that this is going to be O(n) squared in the worst case. And it happens when the insertion sort is already in the reverse sorted order. Right? So just keep this in mind. So best case is O(n) when it's already sorted. Worst case is O(n) squared when the array is in the reverse sorted order. Now, to get a little bit more familiar with this, what we'll do is to look at a couple of examples again. So here, you are given a couple of in-class exercises for you to try and see how many comparisons you need. But before that, let me just revisit this Python library so that you understand that you can actually use it for your own learning. So you just need to download the Python code and to your computer, put it somewhere in your folder, somewhere in your computer, and from that particular folder, you just need to import the respective file. So in this case, so you want to see the animation one, import the animation one. And there should already be an array on a method that is called isort there. Now, if you create an array, for example, it could be some array that you want to sort. And if you want to turn on the animation, you just need to put the flag to true. And then it will have some animation that it will show how, now, at any particular point of time, the purple colored one is the index that we are handling. And then it's going to somehow move all the way to the left. And at some point, it's going to be already sorted. Now, there is another version of the Python code that doesn't have the animation part so that you can just appreciate the actual algorithm itself. All right? Okay, so now, for now, let's take about 10 minutes or so to look at these class exercises. Focus on actually doing this by hand and see whether you can count how many operations you're going to need for these two cases.